when you are fitting any model, let us see that if possible, the model should be linear in parameters, right? Because if it's linear in parameters, then you can use the least square technique, clear? Next point is, once you fit the model, how do you know your model is good or bad? The question is, in many places, almost all, they will say that if the model is good, if the mean square error is less, right? But what I am saying here is, mean square error should not be considered as a criteria to validate a model. Okay? That may be a guideline, but that is not a conclusion. You should not draw any conclusion from that. Why is that? I will tell you now. Before I go here, you see here. Now suppose there is a true signal. I am giving you an example. There is a signal. Actually, you don't know it. That is a sine curve, right? The data which is given to you, it is corrupted by noise, right? Suppose I corrupt this by noise, just showing it like this. This particular data is given to you. The data is corrupted by noise. This is given data. You are given this data, right? Two people I gave the data, this data. The data which is given is the noise data, right? Now they fit the model. See the model. The first person who fitted the model, his model looks like this. The output of the model looks like this. The second person who fit the model, his model looks like this, right? See the given data, you understand? You see the given data is here, like this. Okay, data is here. Now see, if you compare it, the mean square error is less. The mean square error is more. Now can you tell me which one is a good model? The second one or first one? Second one. Because the first one not only fits to the system dynamics, but also fits to the noise present in the data, right? This is the core fitting. This model, it core fits. It core fits. Whereas this one, it captures the system physics. It captures the system physics. And the true model should capture the system physics, the system dynamics, and it should reject the disturbance, right? So if you are using the mean square error to judge the quality of the model, then you are lost, right? So mean square error under any circumstances, it can be used as a guideline. I'm not saying that you completely reject it, but it is not you should not draw any conclusion from that. You have to do many other things, right? See, this example we have given, underfitting, overfitting, you see. If the data is not corrupted by noise, then the mean square error criteria can be used. Mean square error criteria can be used to judge the quality of the model, provided the data is noise-free, it is clean. If data has got some noise, the mean square error criteria should be dumped in the Pacific. Just dump it. It has no meaning. Because you do not know how much noise is there. Because you don't know that. You do not. You see, the day people will know how much noise is there, on the same day our job will go. Noise is there, our job is there. You got a point? Once you know the noise, then matter ends there. Okay? Then you detect the noise, simple line. There is no point of doing any algorithms, image enhancement. Professor Vida Kumar is doing image enhancement. Enhance the image. Lord Sri Krishna has made the Dwarika Puri. Then that image they got, they enhance it. Okay? So noise is a good thing to keep our job, but noise is a bad thing. So mean square criteria should not be used there. Okay. How do you know it? Now suppose in this particular class, there are some idiots, outside people are there. Suppose there are some outside people are there in this particular class, okay? There are 100 people, and there are some people who are outside people. How do you know it? So I will fit a model. I will ask that you fit the model, only capture the system physics, the real people. So he will capture, his model is not perfect. Then he will reject some people. Those people whom model will not capture, I will check whether they are the bloody idiots or they are actually academics. I can check that. Residuals, I will check the property of the residual. I will ask them, do you know about smart grid? What smart grid you are talking about? Okay, then you are useless, go. Okay. Suppose, do you know about signal processing? Yes, signal processing I know. I know about Fourier. Okay, then you go there. Or by wrongly you have come here. Got my point? So the residuals should not have any dynamics. You fit the model, find the residual, check whether the residual has some dynamics. Got a point? The residual should have some dynamics. If the residual has some dynamics, the dynamics must be there in the dynamic model. So you must check the dynamics within the residuals. That is one of the best methods to check whether the model is good or not. In that way, you can check it. Because the data is corrupted by noise, doesn't matter. You just fit the model, find the residuals, and check the dynamics. Okay. How it is, where it's going? Hello? Yes. So model validation, one thing is sure. For you people, I'm telling here, mean square error, if the system data is corrupted by noise, it should be dumped in the RMC. Clear? Clear. Okay? Then you must have different model validation tests, right? And another thing I will tell you, modeling is an art. It has to be learned. It cannot be taught. Programming is an art. It has to be learned. It cannot be taught. What the meaning? You can become good programmer compared to me. Okay, put it. You can become a good programmer, whereas I may not be. Yeah? Good. No, I think those people can fit a model and find out what sort of things are there, then reject the residuals. So all these things, here is a practical example of some noise being generated by my talk. They should find the residuals and the programming. So you guys can do better program, right? Only you can know the syntax. Syntax can be taught. So similarly modeling, I'll tell you just a minute. I've got one doing the modeling. In the laboratory, I remember in England when I was doing PhD, and 14 people are doing. So I've got a friend from Taiwan, JJ Liu. Liu has almost finished his PhD. You see, I'm telling you, almost finished. He's just writing his thesis. Liu is not very good in analytical things. He is good in fitting nonlinear models, very good. So one of my friends is there from Singapore, G. G is now working in A star. A star is just like a DST office in India. A star in Singapore. G is fitting some model, some revolve flow data. Could not fit the model for last so many days. Then G was not coming to the department because he writing thesis at his home. One day I was there and Liu came. Then when Liu came, G called, hey Liu, what the hell you are doing? You are not coming to the department? You are a bloody bastard. This is the usual term. Come. He said, my model is not fitted. Then he said, I don't have time. My car I have parked. It's 1 hour. I paid only £2. No, you come here and you see it's not getting model. It's not getting fitted. Then Liu came. You see how he's done. Like, hey, go. Okay, what is that? Oh, this thing. Just looking like this. Done. 2 months G was doing, could not do it. Liu could do it just by looking, do these things, and he's telling. So that is how I'm saying it is modeling is an art. If you know it, we are surprised. Yeah. Liu always says, he told Swai, Steve never writes excellent student to me. I told many times, Steve, you please write to our government that I am an excellent student. But I have seen he only wrote out of 14 of our PhD students, you and Eduardo. He always writes, Akshay is an excellent student and Eduardo is an excellent student. So he is very jealous of us. Hey, Swai, Steve never writes about myself as an excellent student, but I have seen your recommendation and Eduardo's recommendation. Eduardo is one of my friends, Brazil, he topped Brazilian board and he wrote. So this is Liu. He doesn't know, analytical is not strong, but immediately you will see. And why I am saying it, modeling is an art. You can do it very quickly. Anyhow, mean square error criterion, nothing. Now see, interesting thing. Residual should be uncorrelated. You feed the model, find the residual, and see whether the residuals are noise-like behavior or not. If the residuals, if the patterns remains in the residuals, it indicates that the model has not extracted all available information, leading to biased parameter estimates. Right? Residual should be noise-like property. One of the criteria is cross-validation principle. I'm telling one thing I'm telling, system identification is a difficult subject. What I'm teaching here is a guideline, nothing is conclusive. Don't draw your conclusion from either of them. All combine and apply your brain. Cross-validation, suppose you are given 1,000 data points, keep around 700, 800 data points for your model fitting, and the rest of the things, you use it for model validation, right? That is the cross-validation principle, and the neural network people say that this is a good method. But nowadays people are saying, in your house, your mom has made very nice dishes, all good dishes. See, one of my friends, Luis Agure from Brazil, he told, and he wrote a paper in International Journal of Bifurcation Chaos. Cross-validation, you see the point. Cross-validation, you understand the meaning? You are given 1,000 data points, you feed the model using 700, and the rest 300, you use it validation. Then Luis told one day, your mom has made very beautiful dishes, dinner dishes. You will eat all the dishes, or you will say that there are all 10 dishes you have made. Okay, I will take only 5 dishes today, and the rest 5 you keep it in the fridge. What you will do, your child? You tell me. Your dishes are good. You will take, give me all the dishes, I will take it. Be common sense. And that is agreed by many people. Even David Osterk told the same thing. The cross-validation principle has to be dumped in RBNC. I am collecting 1,000 pairs of data, so let us use it for identification. Why to keep separate? You understand this point? Why to separate it out? Right? So cross-validation principle, although being used, it is not preferred by many people. Again, I am telling you it is not conclusive. That is your judgment. Right? Cross-validation. Because that is the argument. I have got the data, why should not I use the modeling? Right? You should use it. But in your, today in the tutorial, you will given a data sets. So you will separate it in two parts. You will fit one part, another part. This one I will show you now. I have got an argument with one of the professors from IIT Kharagpur who has gone as a visitor to Sheffield University. He has done his PhD from Oxford. I have got an argument, I remember. In the seminar, he was delivering a seminar, and the Kalman filter he was talking and doing some biomedical data. I remember there is a Sri Lankan fellow, Bisa Khan. He is the editor-in-chief of International Journal of System Science. Bisa Khan was there. One step at prediction and model predicted output. You fit a model, and he has done all his work. He has written a book also. I am not naming the name. I am not telling the name. One step ahead prediction to validate the model. Another is the model predicted output. I am writing the equations. See here. You are given a data. You fit a model. You fit a model, theta 1, yk minus 1, plus theta 2, yk minus 2, plus theta 3, uk minus 1. The one step ahead prediction is, you estimate theta 1, theta 2, and theta 3. The one step ahead prediction is equal to theta 1 cap yk minus 1 plus theta 2 cap yk minus 2 plus theta 3 cap uk minus 1. This is the one step ahead prediction. You estimate theta 1, theta 2, theta 3, and if this one is matching, you see the error is yk minus y, one step ahead prediction. This is the error. If this error is less, this model is good. Many people in speech processing, they use this one step ahead prediction. I'm just showing the examples just made. Another way is the model predicted output. I'm writing the equation here. Y cap MPO, model predicted output. I'll show you now, just a minute. It's called theta 1 cap y MPO cap k minus 1 plus theta 2 cap y MPO cap k minus 2 plus theta 3 cap u k minus 1. See the difference? What is the difference? Can you just see the model predicted output is a function of its that prediction output YMPO cap k minus 1, whereas the previous one is just the output yk minus 1, yk minus 2, right? Which one is more rigorous? The second one is more rigorous. The first one is not. Right? Now see, I'm showing the example here. Just a minute. Just a minute, see here. Now, one step ahead prediction of the output. Now, I have got a system I'll show you now. I'll show you, just a minute. Just a minute. This is the system. GS is equal to this one. You identify a discrete model. The system was excited by a PR-based sequence with the amplitude plus minus 3. A total of 800 samples of input-output data were recorded with a sampling period of 1 second. The data was divided into two parts, estimation data set, cross-validation. first 400 samples are which are used for a model estimation and validation data set remaining for model testing. Now, see here common sense. What is the order of the system? What is the order of the system? 3, right? Now for this system, I fitted a model. This model is fitted. How it is fitted, you can do it today. You don't refer that. This is a third order system or second order system? Second order. Why k minus 2? The lag is maximum 2. So this is second order system. K minus 1, k minus 2, uk minus 1, uk minus 2. Right? Then I compute the one-step add prediction. See, it is matching or not? One-step add prediction is this left side. Just see, it is matching. I compute the model predicted output. Matching or not matching? It's not matching. See it here? So one-step add prediction should be dumped where? RFNC. Okay, now see. Next. Then I fit I compute the step response from the model. The step response. I compute the frequency response from the model and the actual, see, not matching. But the one-step add prediction matches. Nothing, all of the things doesn't match. Now come to this point. Third order model. One-step add prediction match. Model predicted match. MPO match. Step response match. Overlapping, right? Frequency response also match. Frequency response also match. So one-step add prediction should not be used to validate the system model. Mean square error should not be used. So you must use the model predicted output. That's a better approach. Certainly a good approach. Right. How many people are working on neural network? In neural network, anybody else? Neural network? Neural network, machine learning. People say machine learning means essential neural network they talk. When the neural network came up, bit of history I'm telling you, everybody in the academic circle started working on neural network. Everybody. Because then they will publish papers. It is a nonlinear mapping. It is essentially nonlinear mapping. It destroys everything. It destroys everything. Only there's a possibility. I'll give an example first, then you will see. Suppose you employ a particular person, and whose job can be done within half an hour. That job requires in half an hour, but you employ him for 8 hours. What he will do? You tell me what he will do. You employ a particular person whose job is he can do for half an hour, the job can be finished. But you are employing him, paying him money for 8 hours. What he will do? He will do his job for half an hour. Then another 7.5 hours in India, he will go and do the gossiping. He will start doing gossiping, all this bloody noise fitting. Fitting to a noise. Okay, fitting to the noise. The variance is more. You understand? Variance is more. Because half an hour job is finished. Then he will go to this side, that office, variance is more. Spread. Okay. Now suppose there is a person, his job requires 10 hours. But you ask him that you do it within 5 hours. Then 10-hour job, if he wants to do within 5 hours, naturally he is stressed, right? So he cannot go out of his seat, yes or no? So the variance is less there, right? Neural network, the problem is, it has got so many degrees of freedom, so many weights. First, the MLP, when it came, the number of layers. First layer, second layer, third layer, anything, okay? 2 layers is fine. Number of weights, okay? And what the neural network will do, 1992, MIT Press published a paper in around 52 pages. You'll find 52 pages. So during that time, I was doing PhD. 94, I started. That paper was published in 1992, MIT Press. Bias variance dilemma. Bias variance dilemma is a complete case with the neural network. Neural network is very prone for the overfitting. It will fit to everything. It will fit the noise, which we don't want, because if it fits the noise, that becomes the problem. You see, once noise enters into a system, it creates a hell of a problem. You know, we are still suffering until now. This, what is that, solar eclipse, lunar eclipse is occurring because of the 2 bloody noise, Rahu and Ketu in Indian scriptures. In the Deva, gods were there. These Rahu and Ketu are 2 demons. They sat, and when the nectar is distributed, they also took it. Now see, this noise enters there. How much problem we are still suffering on that? Every time solar eclipse, lunar eclipse occurs due to those bloody 2 idiots. Right? So you see, if noise enters into the system, that can create havoc. That can create havoc. Neural networks are very prone to fit to the noise. So therefore, they coined many words: generalization capability, bias variance dilemma, all these things came up, and I'm telling you, even until now, we have not solved the problem. The bias variance dilemma problem is still there. I've got a PhD student, he completed PhD, he's now in France doing postdoc, and he joined in Abu Dhabi as one of the academic staff. Faisal Hafiz. Faisal is a very intelligent fellow. We did all the pattern recognition techniques we used in system identification. 2-dimensional particle swarm. We developed an algorithm. Faisal has published around 18 journal papers. In his PhD, he published 12. A very intelligent fellow. He's from Gujarat. He's a Muslim fellow. Does not take non-veg food. No onions, no garlic. Faisal comes to my house, we always go for lunch and everything. Faisal told, no, Dr. Swami, I told, how is possible? He told, my maternal grandfather was a collector in one Jain community in Gujarat. So they don't take garlic and onion, so that practice is still there. Can you imagine in India? He's from Gujarat, and he never takes garlic and onion. He's one of my best students. You can see every day we talk. Still the bias variance dilemma problem is there. And it will continue to be there. It will continue to be there. Neural network, when it came up in 1990, especially MLP network, many people used it for identification, for control. The first control paper in neural network came in IEEE transaction neural network by K.S. Narendra in LA University. I have seen him in one of the American control conference in Orlando. K.S. Narendra at the Singapore conference, first paper came up. Oh dear. You can go to IEEE transaction neural network. K.S. Narendra, there is an Indian girl, student from IIT Chennai. It's a huge thing. Then Steve Billings was there. I was not a student, I was in India. So Steve Billings, what he did, I'm telling the history of the neural network, this system identification. He has got a student from Malaysia, Jamaluddin. Jamaluddin will always come with the traditional Muslim dress in England. I have seen it when I joined. Jamaluddin started, Steve tell, okay, Jamaluddin, this case, Narendra is doing these things. He used the orthogonal least square to fit the weights of the neural network. Do it. Jamaluddin started. Published papers in International Journal of Control. When we went, Steve will say, okay, this neural network should be dumped in the Liverpool Sea. This is completely useless. Steve says that neural network should be dumped. It's not used. But he has published at least 20 PhD students on neural network. The person who is telling it that it should be dumped, he has himself published around 20 PhD students on a neural network. But still, he is telling that neural network should be dumped. My friend, one Nitish Patel, he says, hey, okay, you are telling always against neural network, but your student, I have published papers in neural network, transactions in industrial informatics in some good journals. Then my friend will say, you are a bloody bastard, you are talking one thing, you are doing one thing. I told what I did. Now you are saying neural network is useless, but Chatura is publishing papers in transactions in neural network. I told him, don't ask me, you ask Chatura. See, neural network is good. It has some good practice, but you must be very careful, especially in the model validation. Don't overfit, okay? And this cross-validation, MPO, one-step at prediction, residual analysis, mean square error, you should be used with cautious. Don't use it just like that. But because you have attended this GAN course, this is my sincere request to you. You go to your institute and always tell, I will be very happy, and Professor Rahulkar and Professor Veera Kumar will be happy also, that you say, Akshay Swami from Auckland told that mean square error should be dumped in the Pacific Ocean. No, you say it. And this is the proof. This is the proof. If the data is not corrupted by noise, that's fine. If data is corrupted by noise, it's difficult. Now I show you here. Huh? So bias variance dilemma, difficult problem. Now what we did, an interesting thing, how much time is there? I will tell another interesting thing, which nobody has done in the world. We have done to, our group has done it. Discrete models, this point I'm writing, this is very important. You will also do it in the assignment, tutorial today. Today, I don't know where today or something. Discrete model of a system is not unique. Discrete model, is it coming in the screen? Is not unique. For the same data set, you can get different discrete models with satisfying all criteria. One-step at prediction, MPO, it will satisfy. It is very easy to prove because I have got a differential equation, I change the sampling time, then discrete model will change. Then how do you know? So, this is an important point. Frequency response function. Frequency response function, I'll show you now on the result here, just a minute. Frequency response function is an invariant descriptor of the system. Is an invariant descriptor of the system. These things people don't do it. Entire world nobody does it. Frequency response functions is an invariant descriptor of the system. Even if the discrete models are different, if they are from the same system, the frequency response functions, if you map it, it will be same. I will show you. Interesting thing. Very interesting result. You see, this is the system, typical Duffing's oscillator, y double dot 2 zeta omega and y dot 2 omega and square y to omega and square epsilon yt q. Nonlinear system. I'm not entering into nonlinear frequency response function. Identified discrete models. We identified. How we identify, I'm not telling that. We use some multi-objective algorithms. Poisel did it. Model 1, model 2, model 3. The models are different. You see the coefficient is different. Models are different. Same data set, Same data set, 3 different models, we go fitted it. See the frequency response. See the frequency response. Models looks different, but the frequency response, see the frequency response is matching, right? The nonlinear frequency response is also matching. Okay. So that's, whether I've got other examples or I don't know. So whenever you are fitting the model, many things now, mean square error, one-step prediction, MPO, residual analysis, frequency response matching. Okay? There's so many things taken together, nothing is conclusive. And you have to apply your own brain. So from that, you can imagine how difficult this system identification problem is. It's an extremely difficult problem. It's not an easy task. Therefore, you will find in the world, hardly 5-6 groups are working on system identification. The advantage being, when we are doing PhD, we do not have any rivals. We do not have any rivals because you know nobody is working on that. But if you work in the power system, you have got so many rivals. You have got so many rivals, right? Because that's the point. So you must be very careful while fitting the model. And we'll see, and this one we use it for a multi-objective algorithm. Multi-objective optimization in system identification, multi-objective algorithm in system identification was first started by Peter Fleming from our university in Sheffield. So I have got a friend, his name is Carlos Fonseca. So Carlos was married to a German girl who was doing PhD in statistics. They have got 4 children. His wife is now staying in Germany. We have to meet. I talked with Carlos few months before. Carlos is in Portugal. Carlos Fonseca was doing that job thing, first person. I do not know because Carlos, we go to the coffee shop. What Carlos is doing PhD with Peter Fleming. I went to Rio de Janeiro for a conference in neural network. So there was a special session run by whom people who are working in genetic algorithms must be knowing. Kalyanmoy Dev. Kalyanmoy Dev was working with that, who is the genetic algorithm fellow? David Goldberg or something. Yeah, David something who found out the genetic algorithm. Kalyanmoy Dev was doing PhD under him. So he came to IIT Kanpur, later on he is in Minnesota or something, Michigan. Kalyanmoy Dev with one of his students, a lady fellow from South Africa. So they were presenting many objective optimization problem. Not in identification, many objective optimization problem. Faisal was there. So I told Faisal, let's go to Kalyanmoy Dev, what is talking about many objective, let's go. And when we went, first slide, Kalyanmoy Dev is presenting UOD conference. Photographs of Carlos. I told Carlos photograph, Carlos Fonseca, his name is. You can see the Google. He told, Kalyanmoy Dev is telling, the first person introducing multi-objective optimization in system identification and all these things is Carlos Fonseca. So I was so proud, I thought as Carlos was doing these things. I told Faisal, the Carlos, Eduardo, we are all doing the PhD together in Sheffield University. So the question is, if you work with some big people whose statements matter and people follow it, that matters. So we can tell with full confidence that mean square error should be dumped in the Pacific Ocean. I can tell it. It's recorded, I'll tell it. We have done it, we are doing it, and we will do it. You may say that mean square error, you will use it, and you are useless. Why will you use it to prove it now? Your data is corrupted by noise, how do you know it? You are fitting to the noise or you are fitting to the data, right? Got my point? So I'm telling modeling is an art. These are the criteria, and you should validate the model correctly. And we will see tomorrow when I start telling you the minimum variance control and subsequently adaptive control. The idea is very simple, only 2 minutes I will take it. It is the noise which creates problem. It is the noise which creates the problem. The idea by Carl Ostrom is, if noise is creating the problem, remove the noise. You estimate the noise and remove it. Simple. Idea is very simple. You estimate because you cannot know the noise. Remember, you cannot determine the noise. You can estimate the noise. See the wordings I'm doing. You cannot determine the noise. You can estimate the noise. Okay? You cannot estimate the total noise. You can estimate part of the noise and omit it. We'll see next lecture tomorrow. Have a nice day.